Hey everyone, welcome to my DeepQ Learning tutorial. Here's what to expect from this video. Since DeepQ Learning is a little bit complicated to explain, I'm going to use the Frozen Lake Reinforcement Learning environment. It's a very simple environment, so I'm going to do a quick intro on how the environment works. We'll also quickly answer the question of why we need reinforcement learning on such a simple environment. Next, to navigate the environment, we need to use the Epsilon-Greedy algorithm. Both Q-Learning and DeepQ Learning uses this same algorithm. After we know how to navigate the environment, we're going to take a look at the differences of the output between Q-Learning and DeepQ Learning. In Q-Learning, we're training a Q table. In DeepQ Learning, we're training a DeepQ network. We'll work through how the Q table is trained, then we can see how it is different from training a DeepQ network. In training a DeepQ network, we also need a technique called experience replay. And after we have an idea of how DeepQ learning works, I'm going to walk through the code and also run it and demo it. Just in case you're not familiar with how this environment works, quick recap. So the goal is to get the learning agent to figure out how to get to the goal on the bottom right. The actions that the agent can take is left. Internally, we're going to represent that as 0. Down is 1. Right is 2. Up is 3. In this case, if the agent tries to go left or up, it's just going to stay in place. So in general, if it tries to go off the grid, it's going to stay in the same spot. Internally, we're going to represent each state as this one is 0, this one is 1, 2, 3, 4, 5, 6, all the way to 14, 15. So 16 states total. Each attempt at navigating the map is considered one episode. The episode ends if the agent falls into one of these holes or it reaches the goal. When it reaches the goal, it will receive a reward of 1. All other states have no reward or penalty. Okay, so that's how this environment works. At this point, you might be wondering why we would need reinforcement learning to solve such a simple map. Why not just use a pathfinding algorithm? There is a twist to this environment. There is a flag called is slippery. When set to true, the agent doesn't always execute the action that it intends to. For example, if the agent wants to go right, there's only a 1/3 chance that it will execute this action, and there's a 2/3 chance of it going in an adjacent direction. Now with slippery turned on, pathfinding algorithm will not be able to solve this. In fact, I'm not even sure what algorithm can. That's where reinforcement learning comes in. If I don't know how to solve this, I can just give the agent some incentive and let it figure out how to solve this. So that's where reinforcement learning shines. In terms of how the agent navigates the map, both DeepQ Learning and Q-Learning uses the Epsilon-Greedy algorithm. Basically, we start with a variable called epsilon and set it equal to 1. And then we generate a random number. If the random number is less than epsilon, we pick a random action. Otherwise, we pick the best action that we know of at the moment. And at the end of each episode, we'll decrease epsilon by a little bit at a time. So essentially, we start off with 100% random exploration. And then eventually near the end of training, we're going to be always selecting the best action to take. Before we jump into the details of how the training works between Q-Learning versus DeepQ Learning, let's take a look at what the outcome looks like. For Q-Learning, the output of the training is a Q table, which is nothing more than a 2-dimensional array consisting of 16 states by 4 actions. After training, the whole table is going to be filled with Q values. For example, it might look something like this. So in this case, the agent is at state 0. We look at the table and see what the maximum value is. In this case, it's to go right. So this is the prescribed action. Over at DeepQ Learning, the output is a DeepQ network, which is actually nothing more than a regular feed-forward neural network. This is actually what it looks like, but I think we should switch back to the simplified view. The input layer is going to have 16 nodes. The output layer is going to have 4 nodes. The way that we send an input into the input layer is like this. If the agent is at state 0, we're going to set the first node to 1 and everything else 0. If the agent is at state 1, then the first node is 0 and the second node is 1 and everything else is 0. So this is called one-hot encoding. Just do one more if it's at the last. If we want to put in state 15, then everything are zeros and state 15 is 1. So that's how the input works. With the input, the output that gets calculated are Q values. Now the Q values are not going to look like what's in the Q table, but it might be something similar. Let me throw some numbers in here. Okay, so same thing for this particular input. The best action is the highest Q value. When training a neural network, essentially we're trying to train the weights associated with each one of these lines in the neural network and the bias for all the hidden layers. Now, how do we know how many hidden layers we need? In this case, 1 layer was enough, but you can certainly add more if necessary. And how many nodes do we need in the hidden layer? I tried 16 and it's able to solve the map, so I'm sticking with that, but you can certainly increase or decrease this number to see what happens. Okay, so that's the differences between the output of Q-learning versus deep Q-learning. As the agent navigates the map, it is using the Q-learning formula to calculate the Q values and update the Q table. Now the formula might look a little bit scary, but it's actually not that bad. Let's work through some examples. Let's say our agent is in state 14 and it's going right to get to state 15. We're calculating Q of state 14, action 2, which is this cell. The current value of that cell is 0 because we initialized the whole Q table to 0 at the beginning, plus the learning rate. The learning rate is a hyperparameter that we can set. As an example, I'll just put in 0.01 times the reward. We get a reward of 1 because we reached the goal, plus the discount factor, another parameter that we set. I'll just use 0.9 times the max Q value of the new state. So the max Q value of state 15. Since state 15 is a terminal state, it will never get anything other than zeros in this table. Max is 0. Essentially, these two are gone. Subtracted by the same thing that we had here. Okay, so work through the math. This is just 0.01. So we get 0.01 here. Now let's do another one really quickly. Agent is here, take a right. Q of 13, going to the right. 13 is also all zeros. This is the one we're updating. Here is 0 plus the learning rate times a reward. There is no reward, plus the discount factor times max of the new state, max of state 14. Max of state 14 is 0.01. Subtracted by, again, it's 0. This is equal to 0.009. Okay. It's actually pretty straightforward. Now, how the heck does this formula help find the path? So if we train enough, the theory is that this number is going to be really close to 1. And then the states next to it, it's gonna be 0.9 something. And then the states adjacent to that, it's probably gonna be 0.8 something. And if we keep going, we can see that a path is actually two paths are possible. So mathematically, this is how the path is found. Over at Deep Q Learning, the formula is going to look like this. We set Q equal to the reward if the new state is a terminal state. Otherwise, we set it to this part of the Q Learning formula. Let's see how the formula is going to be used in training. For Deep Q Learning, we actually need two neural networks. Let me walk through the steps. The network on the left is called the policy network. This is the network that we're going to do the training on. The one on the right is called the target network. The target network is the one that makes use of the Deep Q Learning formula. Now let's walk through the steps of training. Step 1 is going to be creation of this policy network. Step 2, we make a copy of the policy network into the target network. So basically we're copying the weights and the bias over here. So both networks are identical. Step number 3, the agent navigates the map as usual. Let's say the agent is here in state 14 and it's going into state 15. Step 3 is just navigation. Now step 4, we input state 14. Remember how we have to encode the input? It's going to look like this. 0, 1, 2, 3, 12, 13, state 14, 15. The input is going to look like this. As you know, neural networks, when it's created, it comes with a random set of weights and bias. So with this input, we're actually going to get an output, even though these values are pretty much meaningless. So we might get some stuff that looks like, I'm just putting in some random numbers. Okay, so these Q values are meaningless. And as a reminder, this is the left action, down, right, and up. Okay, step 5, we do the same thing. We take the exact same input, state 14, and send it into the target network, which will also calculate the exact same numbers because the target network is the same as the policy network currently. Step 6, this is where we calculate the Q value for state 14. We're taking the action of 2 is equal to, since we're going into state 15, it is a terminal state. We set it equal to 1. Step 7. Step 7 is to set the target. Input state 14, output action 2 is this node. We take the value that we calculated up on step 6 and we replace the Q value in the output. Step number 8, we take the target Q values. We'll use it to train the policy network. So this value is the one that's really going to change. As you know, with neural networks, it doesn't go straight to 1. It's gonna go toward that direction. So maybe it'll go to 0.01. But if you repeat the training many times, it will approach 1. Step 9 is to repeat the whole thing again. Of course, we're not gonna create the policy network. We're not gonna make a copy of it. So what we're repeating is steps 3 through 8. Step 10. After a certain number of steps or episodes, we're going to sync the policy network with the target network, which means we're going to make them identical by copying the weight and biases from the policy over to the target network. After syncing the networks, we're going to repeat 9 again, and then repeat 10 until training is done. Okay, so that's generally how Deep Q Learning works. That might have been a little bit complicated, so maybe rewind the video, watch it again, and make sure you understand what's happening. To effectively train a neural network, we need to randomize the training data that we send into the neural network. However, if you remember from steps 3 and 4, the agent takes an action and then we're sending that training data into the neural network. So the question is, how do we randomize the order of a single sample? Well, that's where experience replay comes in. We need a step 3a where we memorize the agent's experience. As the agent navigates the map, we're storing the state that it was in, what action it took, the new state that it reached, if there was a reward or not, and if the new state is a terminal state or not. We take that and insert it into the memory. And the memory is nothing more than a Python deck. How a deck works is that as the deck gets full, whatever at the end gets purged. We need a step 3b. This is the replay step. This is where we take, say, 30 random samples from the deck and then pass it on to step 4 for training. So that's what experience replay is. Before we jump into the code, if you have problems installing Gymnasium, especially on Windows, I got a video for that. I'm not going to walk through the Q-Learning code, but if you are interested in that, jump to my Q-Learning code walkthrough video after watching this one. Also, if you have zero experience with neural networks, you can check out this basic tutorial on neural networks. You also need Pytorch, so head over to pytorch.org and get that installed. The first thing that we do is create the class to represent our DeepQ network. I'm calling it DQN. As mentioned before, a DeepQ network is nothing more than a feed-forward neural network, so there's really nothing special about it. Here I'm using pretty standard way of creating a neural network using Pytorch. If you look up any Pytorch tutorial, you'll probably see something just like this. So since this is not a Pytorch tutorial, I'm not going to spend too much time explaining how Pytorch works. For this class, we have to inherit the neural network module, which requires us to implement two functions, the init function and the forward function. In the init function, I'm passing in the number of nodes in my input state, hidden layer, and output state. Back at our diagram, we're going to have 16 input states. As mentioned before, I'm using 16 in the hidden layer. That's something that you can adjust yourself. And in the output layer, 4 nodes. We declare the hidden layer, which has 16 going into 16, and then the output layer, 16 going into 4. And then the forward function, x is the training data set, and we're sending the training data through the neural network. Again, this is pretty common Pytorch code. Next, we need a class to represent the replay memory. So it's this portion that we're implementing right now. In the init function, we'll pass in a max length and then create the Python deck. In the append function, we're going to append the transition. The transition is this tuple here, state action, new state, reward, and terminated. The sample function will return a random sample of whatever size we want from the memory. And then the length function simply returns the length of the memory. The Frozen Lake DQL class is where we're going to do our training. We set the learning rate and the discount factor. Those are part of the Q-Learning formula. And these are values that you can adjust and play around with. The network sync rate. It's the number of steps the agent takes before syncing the policy and target network. That's the setting for step 10, where we sync the policy and the target network. We set the replay memory size to 1000 and the replay memory sample size to 32. These are also numbers that you can play around with. Next is the loss function and the optimizer. These two are Pytorch variables. For the loss function, I'm simply using the mean square error function. For the optimizer, we'll initialize that at a later time. This actions list is to simply map the action numbers into letters for printing. In the train function, we can specify how many episodes we want to train the agent, whether we want to render the map on screen, and whether we want to turn on the slippery flag. We'll instantiate the Frozen Lake environment and then create a variable to store the number of states. This is going to be 16. And store the number of actions. This is going to be 4. Here we initialize epsilon to 1 and we instantiate the replay memory. This is going to be size of 1000. Now we create the policy DQ network. This is step 1, create the policy network. We also create a target network and copy the weights and bias from the policy network into the target network. So that is step number 2, making the target and policy network identical. Before training, we'll do a printout of the policy network just so we can compare it to the end result. Next, we initialize the optimizer that we declared earlier, and we're simply using the Atom optimizer, passing in the learning rate. We'll use this rewards per episode list to keep track of the rewards collected per episode. We'll also use this epsilon history list to keep track of epsilon decaying over time. We'll use step count to keep track of the number of steps taken. This is used to determine when to sync the policy and target network again. So that is for step 10, the syncing. Next, we'll loop through the number of episodes that were specified when calling the train function. We'll initialize the map, so the agent starts at state 0. We'll initialize the terminated and truncated flag. Terminated is when the agent falls into the hole or reaches the goal. Truncated is when the agent takes more than 200 actions. On such a small map, 4x4, this is probably never going to occur, but we'll keep this anyway. Now we have a while loop checking for the terminated and truncated flag. Keep looping until these conditions are met. This part is basically the Epsilon-Greedy algorithm. If a random number is less than epsilon, we'll just pick a random action. Otherwise, we'll use the policy network to calculate the set of Q values, take the maximum of that, extract that item, and that's going to be the best action. So we have a function here called state to DQN input. Let's jump down there. Remember that we have to take the state and encode it. That's what this function does. This type of encoding here. Okay, let's go back. With Pytorch, if we want to perform a prediction, we should call this torch.nograds so that it doesn't calculate the stuff needed for training. After selecting either a random action or the best action, we'll call the step function to execute the action. When we take that action, it's going to return the new state, whether there is a reward or not, whether it's a terminal state or we got truncated. We take all that information and put it into our memory. So that is step 3A. When we did the Epsilon-Greedy, that was the step 3. After executing the action, we're resetting the state equal to the new state. We increment our step counter. If we received an award, put it on our list. Now we'll check the memory to see if we have enough training data to do optimization on. Also, we want to check if we have collected at least one reward. If we haven't collected any rewards, there's really no point in optimizing the network. If those conditions are met, we use memory.sample and we pass in the batch size, which was 32, and we get a batch of training data out of the memory. We'll pass that training data into the optimize function along with the policy network and the target network. Let's jump over to the optimize function. This first line is just looking at the policy network and getting the number of input nodes. We expect this to be 16. The current queue list and target queue list. So this is the current queue list. This is the target queue list. What I'm about to describe now is step 3b, replaying the experience. So to replay the experience, we're looping through the training data inside the mini batch. Let's jump down here for a moment. So this is step number 4. We're taking the states and passing it into the policy network to calculate the current list of Q values. Step number 4. The output is the list of Q values. Step number 5. We pass in the same thing to the target network. Step 5. We get the Q values out here, which should be the same as the Q values from the policy network. Step number 6 is up here, so reminder of what it looks like. Step 6 is using this formula here. So that's what we have here. If terminated, just return the reward. Otherwise, use that second formula. So now that we have a target, we'll go to step 7. Step 7 is taking the output of step 6 and replacing the respective Q value. And that's what we're doing here. We're replacing the Q value of that particular action with the target that was calculated up above. Step number 8. Step 8 is to take the target values and use that to train the current Q values. So that's what we have here. We're using the loss function, pass in the current set of Q values, plus the target set of Q values. And then this is just standard Pytorch code to optimize the policy network. Now step 9. Step 9 is to repeat steps 3 to 8, starting from navigation to optimizing the network. Basically, that's just continuing this inner while loop of stepping through the states and this outer for loop of stepping through each episode. Step 10 is where we sync the policy network and the target network. And we do that down here. If the number of steps taken is greater than the network sync rate that we set, then we copy the policy network into the target network. And then we reset the step counter. Also, after each episode, we should be decaying the epsilon value. After syncing the network, we repeat step 9 again, which is repeating basically the navigation and training again. So it's just gonna go back up here and do this all over again, all the way until we have finished the number of episodes. So that was training. After training, we close the environment. We can save the policy or the weights and bias into a file. I'm hard coding it here. You can definitely make this more dynamic. Here I'm creating a new graph, and I'm basically graphing the rewards collected per episode. Also, I'm graphing the epsilon history here. After graphing, I'm saving the graphs into an image. Alright, so that was the train function. We already talked about the optimize function. Let me fold that. We already looked at that. Now the test function is going to run the frozen lake environment with the policy that we learned from the train function. We can also pass in a number of episodes and whether we want to turn on slippery or not. So the rest of the code is going to look pretty similar to what we had in the train function. We instantiate the environment, get the number of states and actions, 16 and 4. Here we declare the policy network, load from the file that we saved from training. This is just Pytorch code to switch the policy network to prediction mode or evaluation mode rather than training mode. We'll print the trained policy and then we'll loop over the episodes. We set the agent up top. You've seen this before. Keep looping until the agent gets terminated or truncated. Here we're selecting the best action out of the policy network and executing the action and then close the environment. So ideally when we run this, we're going to see the agent navigate the map and reach the goal. However, if slippery is on, there is no guarantee that the agent is going to solve it in one try. It might take a couple of tries for the agent to solve the map. Alright, down at the main function, we create an instance of the Folsom Lake DQL class. First, we're going to try non-slippery. We'll train it for 1,000 times or 1,000 episodes. We'll run the test 4 times just because the map pops up and goes away when the agent gets to the goal. So we want to run it a couple of times so we actually can see it on the screen. Okay, I'm just hitting Control F5. Alright, training is done and looks like the agent is able to solve the map. We also have a printout of the policy that it's learned. I print it in a way that matches up with the grid. Let's jump back to this in a second. Let's go to our files. So after training, we have a new graph. On the left side, that's the number of rewards collected over the 1,000 episodes. As you can see, over time, it's improving, and finally at the end, it's getting a lot of rewards. On the right side, we can see Epsilon decaying, starting from 1, slowly down to 0. Also, another file that gets created it's a binary file, so we can't really display it, but it contains the weights and biases of the policy network. So if we want to do the test again, we don't need the training. We can comment out the training line and just run this again. And we can see the agent solve the map. We can look at what policy the agent learned. The way this is printed, it matches up with the map. So at state 0, the best action was to go right, which is state 1. At state 1, the best action is to go right again. At state 2, go down. At state 6, go down again. At state 10, go down again. At state 14, go to the right. Okay? So it was right, down, right. So remember earlier that there were 2 possible paths, the one that we actually learned plus the one going down. Because Epsilon-Greedy has a randomness factor, whether the agent learns the top path or the bottom path is just somewhat random. If we train again, maybe it will go down the next time. Now let's turn the slippery factor on. Uncomment the training line. Now with slippery on, we expect the agent to fail a lot more often, or to fall in the holes a lot more often. Let me just triple the number of training. And let me do it 10 times for testing. Okay, I'm running this again. Again, with slippery turned on, there's no guarantee that after training, the agent is gonna be able to pass every episode. Let's make it come up. You see it trying to go to the bottom right, but because of slippery, it just failed right there. But there you go, it was able to solve it. Let's look at the graph. The results compared to the non-slippery surface is significantly worse. Also, you want to be careful getting stuck in spots like these, which means if I was unlucky enough to set my training episodes to maybe 2200 and it gets stuck here, which means it learned a bad policy, it won't be able to solve the map. So in your training, if you're finding that the agent is not able to solve the map when slippery is turned on, it might be because of things like these. Okay, that concludes our DeepQ learning tutorial. I love to hear feedback from you. Was the explanation easy to understand? What can I improve on? And what other topics are you interested in?